The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Okay, I'd like to introduce Mr. Bentz, and he, in combination with Gisera Tanisi and Ahmed Ardani, have put this presentation together. So, go ahead, Bill.
Okay, thank you, Jim. Well, good afternoon, everyone. Let me just throw this over in slideshow. So, some of you may have noticed that I'm wearing my green cements shirt today. I don't know if your fashion approaches are similar to mine. I basically look and see what's available in my closet that my wife has purchased in recent months. And so when I went to the closet a couple weeks ago and this showed up for the first time, it quickly reminded me it was time to get this presentation off to ACI. So I'm going to be talking about enhancing the performance of high-volume fly ash concretes using fine limestone powder. And as Jim mentioned, my co-authors are Gisera Tanisi and Ahmad Ardani, and they're both here in almost up in the front row, so we'll save the difficult questions for them. And I think this has been a really good example. They're with Federal Highway Agency, I'm with NIST, of a government collaboration. We haven't had to do any paperwork, we haven't had to exchange any money. We've just had a research problem that we're both interested in, trying to advance the science and the engineering. So that's kind of my favorite kind of collaboration. So, sustainability versus constructibility. Well, this certainly got a great lead-in this morning. There was the Contractors' Day session that was all about constructibility and sustainability. And basically, we've heard about this in other talks here in the green cement session. I won't go into too many details, but the sustainability is basically pushing us forward to replace the cement in our concrete with other materials. But good old Portland cement concrete has been around for quite a few years, and it's been a very good material. And some of its greatest attributes are that it is accepted, proven, well-known technology, which, as we all know, is very important to our ultra-conservative construction industry, with good reason. It's a material that's known, strong and durable in general. Of course, there's isolated incidents, but in general, when you think about the amount of concrete that goes into place each year and how it performs, that's really quite amazing. It can be expensive to produce relative to some of these options that are coming along, both monetarily because of grinding cost or energy cost, and also environmentally because of the CO2 emissions. And so we've had this increased emphasis, and the question as we move to putting in more supplementary cementitious materials, particularly we're looking at high-volume fly ash, and this was mentioned in just the previous talk, not only do we have to seek out sustainability, we have to maintain the constructibility. Everything that we've been able to do so well with ordinary Portland cement concretes, we really would like to not lose that as we move to these more sustainable mixtures. So some of these constructibility issues, and we've heard about some of these in different talks throughout, even starting from Sunday all the way through to today here at ACI. Incompatibility issues as you start to put more materials into your concretes. So we're using IBP, industrial byproduct, as a generic label as opposed to the SCM that you might be used to seeing. But you can think fly ash when you see that basically for the purpose of this talk. The cement, the fly ashes, the admixtures, they can all play a role. A ready mix producer can be producing a high volume mix that's working quite well. They have to change cement suppliers, they have to change fly ash source, or they have to change chemical admixture brands. It can be a whole new ballgame. They can really have some serious issues, both in terms of either flash setting behavior or retardation where nothing happens for a day. And so that's more the second topic, and mainly this talk is going to focus on the next two, the delayed setting times, which leads to delays in finishing operations. Someone was saying the finishing crew wants to get home for dinner, And if your high volume fly ash concrete is causing a problem with that's a problem that they will notice and they will complain about, and there will be hesitancy to use the material on other jobs. Kind of something that goes along with this is the reduced early age strengths. You got to realize that if you're taking 40 or 50 or 60% of your cement out of your concrete, the cement is generally the most reactive material. And so when you put in that much less cement, you can expect less reaction, less strength at early ages under normal conditions unless you do something to try to account for that. One of the ways that that's accounted for in Portland limestone cements, for instance, when you have the dilution, is you grind finer to get the early age properties up. So the industry is very good at finding ways to get these new concretes to approach the ordinary Portland cement concretes that they're used to. Another constructibility issue can be the increased sensitivity to curing conditions. I've heard some mixed conclusions on this here at this meeting as to whether fly ash concretes need longer curing times or not. But the general consensus, I think, among state DOTs in particular, is that you do need to do extended curing, maybe 14-day curing. Jason Weiss was talking about internal curing this morning for these high-volume fly ash mixtures. And generally, they have a higher temperature sensitivity. Many state DOTs will say after October, you're not going to use fly ash, or you're going to use less fly ash in your concrete, just because we're not sure you're not going to get one of those cold days and the concrete's not going to set for 12 hours. So what am I going to talk about today? This is kind of it's not necessarily a concluding study, but it's the next study in the progression of a series of events that started back in the late 2009 into 2010 timeframe. We were interested in tackling this issue of the delayed setting times in the HVFA mixtures. And so we looked at a lot of different powders that we could blend in to make a ternary blend and try to decrease the setting times. We found calcium hydroxide and rapid set cement at 5 to 10% additions. They were the two most viable options for bringing the set times of a high-volume fly ash mixture back to what we saw in the control ordinary Portland cement concrete. Calcium hydroxide, I should mention, though, that usually comes with about a 15% hit on your 28-day compressive strength. The rapid set cement, on the other hand, produced equivalent or higher 28-day and longer-term strengths. Then just a little beyond that, there was information coming out of NRC Canada, Tai Sato and Jim Baudouin. They were showing that you could really accelerate cement systems, pure Portland, or even with supplementary cementitious materials using nano limestone. So these are limestone particles that are on the order of, say, 100 nanometers, 50 to 100 nanometers. About the same time, there was a research group coming out of Europe that was showing that in a lot of the fly ash systems, you got a very nice synergy. When you had even coarser limestone particles in there, you were getting strength enhancement at 28 days and beyond. That was interesting to us because we had used limestone as one of the fillers in the first study that I talked about that we did at NIST. And while the calcium hydroxide and rapid set cement worked quite well, the limestone that we were using that was about 15 microns in particle size, average particle size, had almost no influence on changing the setting times. So this got us to thinking, and we thought, well, we know nano limestone is doing a lot, the coarse limestone is helping at later ages. What about this whole range that goes between nano and 15 microns? So what if we looked at micrometer-sized limestone powder? We did some studies in the past few years at NIST looking at paste and mortars, and they look quite good. And so then Jasara and Ahmad were willing to try this out in concrete, and that's kind of how this collaboration got started. And so at Federal Highway, they made a series. I think we're up to 15 different mixtures now. I think I'll be presenting 11 or 13 of those today, where we were looking at these ternary blends for sustainable concretes. So what are our variables? We have two levels of cement replacement. Either 40 or 60% of the cement is being taken out of the mix by volume. I'll get to that in a little bit more why we're doing it by volume. We have both a Class C and a Class F fly ash that we're doing this with. The Class C fly ash is a very contrary C ash. It's very reactive. It will flash set with just water, but it won't really develop strength beyond that. It'll liberate a lot of heat and flash set. And then if you put it in a cement system, it'll retard 8-10 hours the hydration. So it's very problematic. It's a very interesting material to try to work with. It has about 25% calcium oxide. The F-ash, on the other hand, is a very well-behaving F-ash, very pozzolanic, only has about 1% calcium oxide. So we wanted to contrast the behavior of those two. We had looked at different finenesses of limestone. For this study, we selected one with a median diameter of about 1 micron. There's another product that's about double that would perform fairly similar to this one. Obviously, the more surface area you're supplying, you might expect to see more benefits or more effect. And so we were working in this study for the concrete with the 1 micron material. And we selected from previous work, we knew that the ratio we wanted to use volumetrically was about 3 to 1. So for our 40% replacement, 30% fly ash, 10% limestone, 60% replacement, 45% fly ash, 15% limestone. So we did this in 2 phases. In phase 1, we made concretes where we maintained constant volumetric proportions. We didn't want to do this at a constant water to cement ratio by mass because of the significant differences in specific gravity between the fly ashes, the limestone, and the cement. So we did everything on a volumetric basis, so all our mixes have the same volumetric water content. So if we see strength effects, if we see durability effects, we know it's not due to the fact that the mixtures have different amounts of porosity because they had different water contents. We kept a constant high-range water reducer dosage for each class of fly ash. So our control system with ordinary Portland cement had 1 dosage. We found with the Class C or the Class F, we were able to reduce that dosage by different amounts, and then we maintained that for any of the mixtures that were made with that particular fly ash. We were very successful, as you'll see, at reducing the setting times back to the controlled concretes. Our early age strengths in some cases were still low, so we went to a phase 2 where we took the typical approach of reducing the water cementitious materials ratio, and we also switched to a type 3 cement to increase early age strengths, just like the industry has been doing for years to go to type 3. You might wonder, I'll just make a side comment about type 3s and setting times. Type 3 cement, if you switch in a high volume fly ash mix, it will help your setting time. We typically wanted to move our setting times by about 4 hours, so we were getting a 4-hour delay. The type 3 would bring us back maybe 1 or an hour and a half of that, so it wasn't sufficient in and of itself. We found the limestone to be much more effective, but certainly if we use limestone and type 3, they're both influencing the setting time. So what we looked at were setting time, strengths, rapid chloride permeability, and surface resistivity. These are the phase 1 mixture proportions. You can see the designation we're using across there at the top. So 40F would be a mixture where we replace 40% of the cement with the F-ash. 30F10L would be the corresponding mix where we took some of the fly ash and replaced it with the limestone. Our Portland cement control mix had 564 pounds per cubic yard, and you can see the dosages of the high-range water reducer here at the bottom. And you can see, indeed, we were able to reduce from 7.7 to either 3.8 or 3 as we went from the Portland cement to the 2 fly ash systems. We had the same amount of water in each mix. Please note once again the constant volumetric proportions, which of course means if we want to report it, our water cementitious materials ratios by mass are not constant. They are different, but we felt it was much more important to keep the same water content. We measured the particle size distributions of each of the starting materials, and then we computationally blended those together to get the mixture values. And the fly ashes were generally a little bit coarser than the cement. The limestone, of course, is finer. So at the proportions that we're using, you can see that certainly there are differences. You know, if we look at either the F-ash up here or the C-ash down here. But we haven't drastically changed the particle size distributions. We're still covering basically the same range, and there is some certainly differences in terms of the find in here with the C-ash and the limestone, but it's not a dramatic change, and that might be one of the reasons we don't see dramatic changes in terms of like slump. We can cut back actually on the water reducers a little bit because of the dilution, taking some cement particles out of the system, and also perhaps the spherical nature of the fly ash. So for the phase 2 concretes, we decided we needed to spec what a minimum 1-day strength that we were looking for. We picked 2,000 psi. And for the 40% replacement mixtures, we decided we would just stick with the type 1-2 cement and cut back on the water. And we did that not by adding more cementitious, but by replacing the water with sand. And those are the water cementitious materials ratios we ended up with for the F and C ash, respectively. And we found that when we did that, taking the water out of the mix, we had to increase the high-range water reducer dosages, and in one case, add in a mid-range water reducer for the F ash. For 60% replacement, replacing water with sand wasn't going to get us there in terms of getting the strengths. So we also switched to a type 3 cement to get the early strengths. And we replaced the water in this case with the blend of ternary powders. And effectively, because then we're putting more powder in, even though we're pulling out 60% of the cement, by the time we increase the powder content, relative to the control, we're not getting a 60% cement reduction, but we are still getting a 50% cement reduction. So let's get into the results. For the setting time, so what we see on your left is the initial setting time, on the right is the final setting times. The control mixture is in red, so we had 224 minutes initial set, 312 for final. What we did to help you kind of classify the data is we put a yellow band on, plus or minus 30 minutes around the control for initial, plus or minus 1 hour around the control for the final. And what you can see is that in general, as we, if we just take an example here, as we add F-ash into the system, our initial set went up to 285 minutes. With the contrary C-ash, it went up to 345 minutes. But in both those cases, when we added the limestone powder in, we easily got back our setting time into the range that we were looking for. The only one that kind of falls a little bit out is this is one of the phase 2 concretes here. It has a setting time of 130 minutes. And that's the one, that's the one where we have the type 3 cement also contributing to the reduction in the setting time. So in the phase 1 concretes, we were able to get all our setting times back into the range that we wanted, and for the most part, other than the 130-minute one there, they were all maintained through the phase 2. So let's look at some of the other properties in terms of strengths. The controls for the Portland cement mixture 1 are on the far left. And you can see the values at 1, 3, 7, and 28 days. And so what we were looking for was we wanted to get the 2,000 psi at 1 day. That was our target. And we wanted to be 90% of the controls at 3, 7, and 28 as a minimum. And you can see the different mixtures that met or did not meet those criteria. Basically, we found that the phase 2 concretes, the water cement ratio reductions, or switching to the type 3 cement were sufficient to meet the strength criteria. We also did a cost analysis because that's very important for ready mix producers in the real world. They would like to know, is this concrete going to cost them more or less? I would point to the 5 boxes that are in yellow. That's the control and the 4 phase 2 concretes, and there we put the strength on a cost per unit volume per unit strength basis. So to get equivalent strengths, and you can see that 3 of the 4 phase 2 concretes are definitely more economical than the initial concrete, and the other one is basically a wash, $1.51 versus $1.56 in terms of meters cubed per megapascal. Strange units, but you can just compare the numbers. So these concretes are very economical because the fly ash is much cheaper than the cement. The limestone powder is somewhere in between the two, so overall you can save some money. I'll just quickly go through the transport results. Gary Knight mentioned earlier today that he's seen some really good results when you put limestone in with fly ash systems. We're seeing the same thing here. We can just focus in on the rapid chloride permeability numbers. We have the control at about 2,500. These are at 56 days. And then we can see that as we move, I don't seem to be able to get my pointer anymore, but putting the fly ash in and of itself reduces it, and in every case, when we put in the limestone with the fly ash, like we have 2109, it's cut down to 1199. We see about a 50% reduction in terms of the limestone and the fly ash really working synergistically together. We see the same thing for surface resistivity. I won't go over those. An interesting thing is that when you plot strength versus resistivity or strength versus rapid chloride, there's not really any clear trend there. So if you're proportioning for strength or you're proportioning for durability, those are two different things. And I think that's been something that's been preached in recent years by many parties. So why are we seeing these effects? We went back and did calorimetry work, and we can definitely see the acceleration that is provided by the limestone. The fine limestone, particularly the surface area, is important. It's providing additional surfaces for the precipitation and growth of reaction products. There are some indications that the CSH likes to precipitate on the limestone particles even more than it likes to precipitate on the tricalcium silicate and dicalcium silicate that are in the system to start. The limestone does participate in the reactions and form some carboaluminate phases, and Montero and his group in California have shown that those phases can actually be stiffer than ettringite or sulfoaluminates. So that could be another reason to get increased strength. When you look at durability, the limestone's accelerating the reaction. You have more hydration. The carboaluminates take up more space, so you're cutting down your porosity. You're also diluting the conductivity of the pore solution because you have less alkalis going in, or you have alkalis being absorbed by the pozzolanic products that are formed with the fly ash. And it's well known that the fly ash tends to further refine the pore structure and give you lower diffusion coefficients. So overall, we found that we could indeed mitigate the setting time delays, just like we saw in our paste and mortars in the concretes. And the other benefits that we're seeing, very good benefits in terms of increased early age all the way through 28-day strengths, likely beyond. We haven't measured those, but we anticipate that they will be higher. Improved transport coefficients at 56 days, and they are sustainable because they are both economically and environmentally favorable relative to 100% OPC concrete. So we're doing some more work with the Phase 2 concretes. We got very high one-day strengths with our Type 3 cement, so we've actually kind of backed off a bit on our cement contents and increased our water-cement ratios a little bit to try another round of those. I want to thank everybody that was willing to supply us with materials. Always appreciated. And any questions?